Sushruta for NEET is now available on the Google Play Store. Try it out for free.
Hello students, good morning. In our last lecture, we learned about few basic terms, common terms that we use in coordination chemistry, and these terms are some of the terms are here. I'll just briefly name them. And there's a coordination entity. The coordination entity it constitutes central metal as well as ligand, and it is the entire thing is written in a square bracket. Coordination entity could be cationic, anionic, or neutral. These things we know. The central metal, this is the central metal, for example, in this case, this is the central metal. Rest all the groups that you see, they are all the ligands. So ligands are central atom, this could be central atom or central atom ion. It could be in the ionic form. As in this case, cobalt is in plus 3 oxidation state, so it is cobalt plus 3 plus ion. Then we show ligands. Ligands could be of different types. So there are many definitions of then there are many different type of classification of ligands. So ligands usually we can classify ligands into unidentate or monodentate, bidentate or polydentate. Monodentate or unidentate means the ligand has only one donor atom. Bidentate means ligand has two donor atoms which can coordinate with the metal or which is coordinating with the metals, and the ligand is bidentate. And then after that we say polydentate commonly, but it could be tridentate, tetradentate, pentadentate, hexadentate, heptadentate, octadentate like this. So that all those ligands are commonly called as a polydentate ligand. Ligand could also be ambidentate. The definition I have seen that the same ligand has two donor atoms. However, at a given time, only one coordinates to the metal. Maybe in another complex, some other atom, the another atom which is also which will coordinate with the metal. So there are two different donor atoms in the same ligand, but at a given time, only one coordinates to the metal. Then such ligands are called ambidentate ligand. Then we also saw about the chelating ligand. And chelating ligand, these ligands are what? They are bidentate or for the polydentate ligands, are having two different donor groups. And if all the donor groups are at least two donor groups coordinates to the same metal at a given time, then such assembly is called chelate or the chelation, and the ligand is called chelating ligand. And because of the chelation, what we see, the stability of the complex increases, and the reason behind this is the entropy that I have already described. So these are the basic definitions we have already seen. The examples are also shown here. Now chelating ligand, this porphyrin or the complexes which are called complexes of porphyrin which are called porphyrins. You see, they are all chelating ligand or chelating complex. In these cases, the examples are hemoglobin, this heme part, chelating ligand is there. This porphyrin complexes make to the iron plus 2 oxidation state, and iron goes into plus 3 oxidation state once oxygen binds to it, and those things are, and that is how the oxygen is carried from lungs to the tissues. Here, this is the chlorophyll. Chlorophyll's structure. It also has porphyrins, and the porphyrins is there. The metal here is magnesium, and two types of chlorophyll that we know: chlorophyll A and chlorophyll B. The difference only is here in the R group. If it is CH3, it is chlorophyll A. If it is CHO, it is chlorophyll B. Then some other kind of complexes we have also seen, which are found in nature. Then another kind of classifications of the ligand is hapticity, of that we also call the hapticity of the ligand. And hapticity means if the ligand has how many consecutive atoms are there in the metal which are coordinating there in the ligand which are coordinating to the metal. For example, if there is only one donor atom which is coordinating to the metal, then the ligand is called monohaptic ligand. If there are two consecutive atoms or contiguous atoms which are coordinating to the metal in the given complex, then it is called dihaptic complex, and it is represented as eta. Uh, Eta, and this I forgot to mention this one. The denticity, this is called denticity, and this is represented as kappa. That K, see this letter. Greek letter which is similar to K, kappa. This is represented as eta. So this is eta 2. Eta 2, this is ethene coordinating both the carbon atoms are now forming bond with the metal. And so this is eta 2. In this case also we see the eta 2 ligand. This is propylene, and propylene only two carbon atoms coordinate to the metal, and so this eta 2 complex. Eta 2 means the hapticity of the ligand is 2. It is dihaptic ligand, this propylene. And this allylic radical, if allylic free radical is there, there is what how the allylic free radical will be formed. It is just one hydrogen atom departs away from the center with its own electron, and the one electron that was in sharing, that is part of that was part of this carbon atom is, if there is a CH bond, one to that CH bond, one electron is given by the carbon and another electron is given by the hydrogen atom. So if hydrogen departs away from its own hydrogen, one electron, then there will be one odd electron on the carbon, and that's called radical. This is how the radicals are formed because of the homolytic cleavage. What is homolytic cleavage? In details, we have already seen in organic chemistry. And so this will form allylic free radical. So there will be one coordination center at this carbon atom and two coordination centers are at these two carbon atoms. And these all three carbon atoms are in a line. They are directly connected to each other, and this is called contiguous atoms. So three contiguous atoms, and so this eta 3 complex. This you see dibutene, dibutene it is eta 4 because all the carbon atoms are now coordinated to the metal here. So this is eta 4 complex. This is cyclopentadienyl anion, cyclopentadiene you can see, and if you just remove one hydrogen which its lone pair, sorry, with its own shared pair of electron, then there will be one odd electron on this carbon atom which was shared with the hydrogen atom, and that odd electron, and now the two, this is a pi bond. The pi bond, each carbon atom now will be sharing one electron. The pi bond will be broken out if there is enough back bonding or something that is not there. So in what we see, all the carbon atoms are now coordinating to the metal, and they are all contiguous carbon atoms. They are in continuation. They are so this is called eta 5 complex. Then it means it is pentahaptic complex. If benzene ring coordinates to any metal, if benzene ring coordinates to any metal, then what we will see in that case, it will be hexahaptic complex. So the ligand will be called uh, hexahaptic ligand. This is cyclopentadienyl. In this case, it is behaving as a pentahaptic ligand. Now, there is another classification of ligand, the terminal ligand and bridging ligand. The terminal ligand, all this ligand is terminal ligand. These ligands are also terminal ligands because they are bound to only one metal. But if one ligand is bound to two different metals, then these two different metals, it doesn't mean this two, here it is two different atoms, I should say. It should not be this ruthenium. It can be both ruthenium or both iron or both copper. However, or maybe it can be one ruthenium, in this case iron. So if two different atoms, it is metal atoms. If one ligand is coordinated means at least two different metal center. Then it is called bridging ligand. It can coordinate to three same atom, same donor atom can coordinate to even three centers. So in that case also it will be it will be having as a bridging ligand. So here chlorine is what the bridging ligand, bridging chlorine ligand in this case, and this chlorine is the terminal chlorine ligand, and this bridging ligands are represented with the Greek letter mu that you can see here. Then we saw other terms, oxidation number of central atom, oxidation number. We remove the ligands with the third pair of electrons, means all the bonded electrons, and remove the ligand with the bonded electrons or the coordinated electrons, and whatever the charge that will appear on the central metal is called oxidation number of the central metal or the central atom. Then the coordination sphere, we know coordination sphere and the coordination entity, they are same. We have seen this one. Mhm. Just a minute. And then we looked up Then we studied about the coordination number. The coordination number is what? How many donor atoms are directly coordinating to metal, means directly linked to metal, directly bound to metal. It's called coordination number. An example in this complex, if you look at six CN groups, and this all the CN groups are actually this is bound to the metal iron through carbon atoms. So six carbon atoms are there through six cyanide cyanide ligands or cyanoligand, and that is why the coordination number in this case is 6. In this case, coordination number of this nickel metal is 4. Here, the iron is the metal. In this case, platinum, the coordination number of the platinum in this complex is 4, and so on. Then we looked at the homoleptic and heteroleptic leptic complexes. Homoleptic complexes means all the ligands are same, and heteroleptic complexes means ligands are different. Then finally we saw this definition, coordination polyhedron. So coordination polyhedron talks about the arrangement of ligand around the central metal and how the ligands are arranged, in what shape they are arranged, and that is what we call the coordination polyhedron. Usually, typically there are three coordination polyhedron that are found abundant in the nature, and that is called the octahedral or the tetrahedral and the square planar. These are three abundant mm, coordination polyhedron. However, in some cases, this trigonal bipyramidal and a square planar, a square pyramidal are also being seen. The square planar is already here. Now let us look into the nomenclature of coordination compounds. So we have seen the nomenclature of organic compounds as well in organic chemistry, and the whatever the rules that we studied there also the given by recommended by IUPAC, here also the nomenclature in naming the coordination compound. We follow the rules, we follow the conditions or the criteria recommended by IUPAC, International Union of Pure and Applied Chemistry, the full form of IUPAC. So a systematic method of naming of coordination compounds like the organic compounds is also important, because many different types of coordination compounds are being synthesized using same metal and the same ligand. And so this is for the unambiguous description of the formulas. So once you, the, so it means just by looking at the name, you should exactly understand what will be the chemical formula of the metal, and not only the chemical formula, you should also have the idea what will be the structure of the metal, and that you should have this idea unambiguously. There will be no ambiguity, that no possibility, second possibility of the structure. And this unambiguous representation becomes more important in the case of isomers, because what we know in the case of isomers, even if you write one molecular formula, but a structure can be different. And that while naming coordination compounds, so their names should be such written uniquely in such a way that you can just write one structure of one isomer and not the other one. So, a systematic method of nomenclature of coordination compounds is essential for an unambiguous description of formulas. It becomes more important while dealing with isomers. The procedures adopted for naming coordination entities are based on the recommendations of International Union of Pure and Applied Chemistry, that is IPSC. Let us now look into the formulas of mononuclear coordination entities. This is only in your syllabus. So only we will first, before going into the naming IUPAC nomenclature, we'll first learn how one can write the formula of mononuclear coordination compound or the coordination entities. And a mononuclear means what? Only one metal will be there. The dinuclear or binuclear means two metal centers are there. And if the two metal centers are there in the same coordination compound, as you can see here in this case, two metal centers are there. This is a binuclear coordination complex. And in the binuclear coordination complex, we need a bridging ligand at least so that it gets bridged. Or there could be another possibility that there is a metal-metal bond between two metals. Or if this chlorine is not there, if there is a ruthenium-ruthenium bond, and without chlorine, so there are certain possibilities, so that either there is a bridging ligand or there is a metal-metal bond, then only we will see binuclear complexes, and the mononuclear complexes, all other than this complex, whatever the complexes that we have seen till now, they are all mononuclear complexes. Although in this case there are two metals, but this metal is not part of the coordination entity. Only this is ApCN6 4 minus is the coordination entity, as you can see here. This in this case, this is PTC, this is a coordination entity, this is coordination entity, and it's all the cases here. So you can see the only one metal is there. Here the same structure is this. So all you can see the mononuclear, they're all mononuclear complexes. So we will mostly be focusing on the mononuclear coordination entities. The formula of a compound is shorthand tool, and this is what we know. A chemical formula of a compound, any kind of compound, is a shorthand tool which is used to concisely provide basic information about its constitution. Its constitution is what are the different elements or what are the different chemical entities which is forming this given compound. And to make that clear, we use the chemical formula to represent the entire chemical composition of the given compound. And if you can write this chemical formula, and so there are certain rules to write chemical formula for the coordination compounds as well. Although one thing is important, people don't stick to these rules while writing the chemical formula of coordination compound. However, writing the IUPAC nomenclature, you have to follow the certain rules only. In that case, there will be no liberty. There you cannot avoid the rules or the procedure recommended by IUPAC. In writing for the chemical formula, people sometimes they also avoid those rules that are recommended by IUPAC, but that is pardonable. But you cannot do the similar mistakes in writing IUPAC nomenclature. I just show where we depart in those cases. Anyway, so what are the rules for writing the molecular formula or the ionic formula about the chemical formula of coordination compound or the coordination entities are these. So mononuclear coordination entities contain a single central metal atom which I have just described. The following rules are applied. The first rule is what you will have to write the central atom first. You will start a square bracket and then you will write the central metal first. Then the symbols of different ligands will be written after the symbol of the central metal. So we start with the square bracket. We will open the square bracket and write the symbol of the central metal, and then we'll write the symbols of the ligands, and that the symbol of the ligand should be written in the alphabetical order. So whatever the chemical formula of the ligand will be there, and that whatever that we use, the first letter we will compare for the alphabetical order. For example, if you write this, and so anyway, that we'll see later on. So this is polydentate, and in the case of polydentate ligand, so the ligand, their names are listed in alphabetical order. The polydentate ligands are also listed alphabetically. So in the case of polydentate ligand, what happens? We also write them alphabetically. However, sometimes what happens is in the case of polydentate ligand, we use, even in the case of monodentate ligand, if the name is very big, so we use abbreviation. And even these abbreviations are used for considering the alphabetical order. For example, this is the ethylene diamine. The ethylene diamine we consider E for to decide its place in the alphabetical order. Because EN it represents ethylene diamine, so we don't see entire structure, we only see the abbreviation. So polydentate ligands are also listed alphabetically. In the case of abbreviated ligands, the first letter of the abbreviation is used to determine the position of the ligand in the order. Here in this case, H2, water is written always as H2, so hydrogen will be, each will be considered for the alphabetical order. So in the case of abbreviated ligand, again I am repeating it, the first letter of the abbreviation is used, as I said, T will be used to determine the position of ligand in the alphabetical order. The formula for the entire coordination entity, whether charged or not, is enclosed in a square bracket. So once you have started the square bracket, then within the central metal, and then all the ligands, the symbols of the ligands in alphabetical order. And once you finish this, you have to close that square bracket. So you started with this metal, ligand, and then you have to close this square bracket. And if there is any charge on this coordination entity, then you will have to write the charge on the superscript, right superscript of the coordination entity, means just after the closing of the square bracket. Just above it, you will have to show the charge of the coordination entity. Whether it is positively charged, then you will have to show positive charge on it. If the charge is, then in that case, what will you like? The numerical number first, and then we write the charge. If it is a single charge, we just write single plus, single positive charge, and if it is two plus charge or plus plus charge, then we write two first, then plus. If three plus charge, then we write three, then plus. And if it is negatively charged, so we suppose there is three negative charge, so we write three and then minus as a superscript, right superscript. And why three minus, not minus three? Because minus three is written. This is the general convention, which only it depicts the oxidation number. It doesn't depict the real charge. And in the case of coordination entities, whatever if there is charge, those charges are real charges. And so we'll have to show the numerical number first, and then the nature of the charge we'll have to show. So the formula of the entire coordination entity, whether charged or not, and even if it is neutral electrically neutral, you don't have to show the charge. But this formula of of the neutral coordination entity also should be enclosed in the square bracket. If the ligand is polyatomic, its formula is enclosed in parentheses, and the ligand for this is a polyatomic ligand. It contains hydrogen and oxygen, two different atoms. Means three atoms, it contains three atoms. So that is formula in the coordination entity or the coordination sphere will be closed in the parenthesis, the small bracket that we call the small bracket parenthesis. And then how many number of such, what is the number of such ligands will be also written at the subscript, the right subscript. And the simply another, the ligands abbreviation are also included in parentheses. And if the ligand abbreviation are used, like EN is a ligand abbreviation, and this will also be written in the parentheses. And how many numbers of such ligands are there, that will be shown as the right subscript. This is the right subscript. The below is if it is, and the subscript if it is above, it is called superscript, and the right means on the right hand side. Like if the EDTA is there, you will also have to write EDTA in the parentheses. There should be no space between ligands and the metal within the coordination sphere. We don't provide any space while writing the name, uh, writing the symbols of metals and the and the ligands, other ligands in coordination sphere. As you can see here, we have not provided any space anywhere. In all the examples, there is no space while writing chemical formula of any coordination compound. So we should note there should be no space between the ligand and the metal within a coordination sphere. Then the next rule is when the formula of a charge coordination entity is written without the counter ion, the charge is integrated outside the square bracket, as I said earlier. This charge, if the coordination entity is charged, and you are writing the formula of this coordination of the complex compound without the counter ion, then what we will have to we will have to show the charge on the coordination entity, and this charge, the charge is integrated outside the square bracket as a right superscript with the number before the sign. The number, then the sign in the superscript. Example, you can see this is a coordination entity, anionic coordination entity, and the anionic coordination entity, its counter ion will be the cation. For example, if you can write here K3, CuCN6, CuCN6 will be in the square bracket. This is some chemical compound. If you are not showing counter ion K3, means 3 potassium ions, then you will have to show 3 negative charge on this coordination entity as shown here. It will be shown after the square bracket as a right superscript. And in right superscript, you see the numerical number. The number is written before the sign, negative. This is the cationic coordination entity. And in the cationic coordination entity, what is written here again after the square bracket, the charge is shown, and in that also the number is written before the sign as a in the superscript. And what is the counter ion? In this case, the counter ion in this case could be chloride, C3 chloride ion. So the real compound will be the chemical formula of the real compound will be CrH2O whole 6 in a square bracket Cl3. And if you are showing Cl3, then in that case you don't have to show this 3 plus charge. And if you are showing anyway 3 plus charge on the coordination entity, then in that case you will have to write this as 3Cl minus to show that this chemical formula, the entire thing is actually electrically neutral, and this is what happens in reality. This will not found independently in nature. It will always be associated in any system with its counter ion. You cannot have only this solution or only this complex anywhere. You cannot synthesize it. It will always be synthesized with the counter ion. This will also be always synthesized with the counter ion. It will exist in nature with its counter ion, whether in solution also. The counter ion will be there. Although those counter ions will be ionized in aqueous medium and they will be here and there scattered, but the number of the charge, the net charge of the entire system is always should always be zero. This is what we already know. And the same thing we should also remember here as well. The charge, the next point is the charge of the cation is balanced by the charge of the anion and vice versa. So the same thing here, as I said, the charge of the cation, this is the cation, is to be balanced by the charge of anion. There is 3 plus charge, so your ligand should have either if the phosphate, if the counter ion is phosphate, PO4 3 minus. One can have PO4 3 minus as the counter ion, and so the charge is balanced. Or if the chloride ions are there, you should add 3 chloride ions to balance 3 positive charge. Similarly, here this is the anionic species, so we should have 3 potassium ions. Or if the aluminium is there, only one aluminium 3 plus ion will work for this. And so, for example, the charge of the cation is balanced by the charge of the anion and vice versa. Here example we have already seen. Let us see these examples. This example. So this is cationic. COCl whole 5. This is cationic, and you can see this is a polyatomic ligand, and that is why it is shown in parenthesis. There are 3 hydrogen atoms and 1 nitrogen atom. So it is actually tetraatomic, means it's a polyatomic ion. So it is shown in parenthesis while writing the molecular formula. This is also you can see here. However, this is not polyatomic. It is just a Cl. Ligand is only Cl. One atom is there. Although two such ligands are there that it represents the number of ligands. If Cl2 doesn't represent that it is Cl2 molecule, it's not Cl2 molecule. It is actually two chloride ions. So this is monoatomic ligand, and that is why it is not shown in parenthesis in this case. Anyway, now let us look at this. There is a 2 plus charge on this coordination entity because 2 chloride ions are there to balance it. So there is 2 plus charge, and so that plus charge is now balanced by 2 chloride ions. In this case, one complex must be cationic, another complex must be anionic. And suppose if the nickel is in zero oxidation state in this this coordination entity, there is just a minor error. This one should also be in the square bracket. So this is one coordination entity, and this coordination entity usually when we write the formula of an ionic compound, we write cations first and then the anions. And that if it is written as such, it means you should understand that this is anionic and this is cationic. So there must be a positive charge on it, a negative charge on it. If there is no positive negative charge, you cannot write them. They will be separate complexes. They are not same compound. They're not part of the same compound, but if since they are written as together, means they're part of the same compound also. And this must be cationic, this must be anionic. And how this will be cation and this will be anionic? Suppose if I consider nickel in zero oxidation state. So there are two chloride ions, and two chloride ions, each chlorine has one negative charge. So two chloride ions having two negative charges. Nickel has zero charge, water has zero charge, four water molecules will have zero charge. And so the net charge on this entire coordination entity will be 2 minus. In this case, there is 2 minus, and to balance it, there must be 2 plus charge on this cation. And that because the entire compound is written with no charge, it means the charge on this cation is balanced by the charge on this anion. And it means the platinum here is in plus 4 oxidation state. And how it is, let me describe. So chlorine here, each chlorine has one negative charge, so two negative charge, two chlorine, ammonia neutral. And the two negative charge for chlorine and platinum must be having four charge on it, plus four charge, or means the platinum must be in plus four oxidation state. So that even if the two plus two oxidation state of this platinum is neutralized by two chlorine atoms, then it will have net plus two charge to balance net two negative charge on this coordination entity, anionic coordination entity. So this is anionic coordination entity, this is cationic coordination entity, and in this compound, the charge on this cationic coordination entity must be equal to the charge of the anionic coordination entity. And so I would expect this is has plus, this is has been two minus charge, this is having two plus charge, and the nickel here is in zero oxidation state, platinum here is in plus four oxidation state. Then only this will be possible. Another possibility is also there, but that is highly unlikely. If you understand the chemistry or the possible oxidation state, usually, so nickel, suppose nickel here is plus one oxidation state. If the nickel is in plus one oxidation state, then two chlorine, this entire thing will be two chlorine ions are there, two chloride ions are there, and nickel plus one, two chloride minus two, so there will be minus one charge on it. And then that case, platinum is having suppose plus three oxidation state, is having plus three charge, and two chlorine atoms. So plus three and minus two, there will be plus one charge on it. So this coordination entity is the cationic is having plus one charge, is having minus one charge. This is also another possibility one can think of. Let us now look into some examples. Write the formula for the following compounds. So we have to write the formula of these compounds. The pentaamine chlorocobalt 3 sulfate. So what is pentaamine? Chloro or chlorido cobalt 3 sulfate. So what is the metal is cobalt. So we will start with the square bracket. Open the square bracket. We will write the metal. So symbol cobalt CO. Then what we will write? There are two ligands, chlorine and amine. And the chlorine, if I'll have to write the chlorine, C comes first. So C chlorine we will write first. And this is a monochloro. This is there is only one chlorine. It is not written di or tri. It means only one chlorine is there. And the pentaamine. Amine is actually the name that is recommended for a ligand. The ligand is ammonia in this case. If ammonia is the ligand, then we call it as amine while writing this. The name amine of the ammonia ligand is recommended by UPSC. So this amine represents ammonia, and how many ammonia are there? Pentaamine. So five ammonia molecules are there, and ammonia is polyatomic ligand. So we'll write it in a square, write it in parentheses, and the parenthesis is closed, and the five, which represents this five represents five amine ligands, amine ligands means ammonia ligand is there. Means five molecules of ammonia is there. And then this complex is over, we will have to close the square bracket and the space is there and then sulfate. It means the sulfate here is the counter ion and the counter ion there is a space. So this is counter ion, so that is why square bracket is closed here and the sulfate SO4 represents the counter ion that is here. And it means the sulfate has minus 2 charge. It means this coordination entity must be having plus 2 charge on it. So if you remove this sulfate ion from there, in that case you will have to show plus 2 charge on this coordination entity. And that means the cobalt here is in plus 3 oxidation state. Why? Because if you remove ammonia, it will parts away with its lone pair of electrons, which is on the nitrogen. So it will parts away because nitrogen is. However, this is chloride. The chlorine, only chlorine atom gives only one electron. It says one get one electron from the cobalt, and this is one way to understand this. And so, what will the two electrons are there in the sharing, and the this when the chlorine parts away, it will take both the electrons of the shared pair of of electrons, and so there will be charge on this as well. So there will be one extra charge on the cobalt because of this. So anyway, so what does it means? That cobalt must be having plus three oxidation, must be plus three oxidation state here. And how it is because if cobalt has plus three charge on it, one charge will be balanced neutralized by one chloride ion. The charge on the one chloride ion. So this will become the net charge plus two, and that net charge plus two charge is balanced by one sulfate ion. Now let's see this example. Tricarbonyl. So this is carbonyl. Carbonyl is the main ligand. It's the carbonyl means the carbon monoxide is the what acting as a ligand in this case. Chloro. Then one chloro is also there, and the chloro is also written as chlorido. So the one chloride ligand is there. One carbon. The tricarbonyl. Three carbonyl ligands are there. With the name, we will just one and two chloro. Dichloro means two chlorine. There are two chloride ions are there. And then what? Bis triphenylphosphine. Then this is triphenylphosphine, and triphenylphosphine is what? It is a ligand, and the this represents here two. So two triphenylphosphine ligands are there. So what we will write? So if it is there a tricarbonyl, there is a mistake in this name. It is three here. Yes. So what we will again what we will do? The same thing will follow. We will open a square bracket, write the name of molybdenum means the metal, symbol of the metal, molybdenum MO. Then we'll write the symbols of different ligands. The chlorine is written as Cl, carbonyl it is Cu, and the triphenylphosphine it is PPH3, and PPH3 phosphorus. And then if you look at in the look into the alphabetical order, the chlorine will come first, so it is Cl2 dichloro, so we'll have to write Cl2 tricarbonyl, then the CO, this is polyatomic, and this anyway CO, and then this three tricarbonyl, three subscript to represent three CO groups are three CO ligands are there, and then PPH3 twice. This represents two, and triphenylphosphine. This is triphenylphosphine. Phosphine is pH3, and if you remove all the hydrogens of phosphine with one phenyl group, this is pH written as pH in shorthand notation. And so three hydrogen with three pH groups, so it will become PPH3, and so it is triphenylphosphine. And this recommendation, this say we write this triphenylphosphine because tri is already there. And if you write ditriphenyl, it will be confusing. It won't look good. So to differentiate between these, what we do in the case of the ligands, which also contains numerical prefixes in its name anywhere, in the case that case, to represent the number of such ligands, these trees, tetrakis, pentakis, etc. are used in the places of di, tri, tetra, penta, and so on. So this represents di. Two. Trees means three. Tri. Tetrakis represents four. Tetra means four we know. And in that case of tetra we also have. Pentakis five and so on. Now we have seen this example how one can write the molecular or the chemical formula of mononuclear coordination compounds or coordination entities. Now let us look into the IUPAC nomenclature of mononuclear coordination compounds. And there are again certain rules we have to follow, and those rules, those procedures are recommended by IUPAC, is universally accepted, all over the world, and it is followed as well. So let us look at those rules. The names first of the or of mononuclear. Mononuclear again it means only one central metal is there or central ion is there, central atom is there. Central metal, central atom, central ion. Okay. So the names of mononuclear coordination compounds are derived by following the principles of additive nomenclature. This is the principles of additive nomenclature. This is recommended by UPSC. What does it mean? The ligands that surround the central atom must be identified in the name. So whenever you are writing the name, like as you see, this name is actually as per the IUP. These are the IUPs in naming of these two compounds, both the cases, and in both the cases, while explaining to how to write the chemical formula, I actually identified what are the ligands that are there, like carbonyl, fluoro, triphenylphosphine. So what we'll have to do while writing the IUPAC name of such compounds, we should write the names in such a way that one can easily identify or recognize which ligand is there in this coordination compound or coordination entity. So names should be written in such a way. And then what happens? They are listed as prefixes, and the name of these ligands are listed as prefixes. While writing name, the name of the metal we write last. At last, we write the names of the ligands first. However, when writing chemical formula, we write the metal first and ligands later. This you can see here. Metal first in chemical formula, then ligands in alphabetical order. However, in writing IUPAC name, we write ligands in alphabetical order, their names of the ligands in alphabetical order first, and then the name of the metal. This is what the rule that we follow. So they are listed as prefixes. The names of these ligands are listed written as prefixes to the name of central atom, along with any appropriate multiplier. An appropriate multiplier means what is the number of a particular type of ligands that is there in the given complex entity or complex compound. Whether the same ligand is repeated multiple times or not, or same ligand means the homoleptic, heteroleptic that we have seen. The kind of homoleptic complex is only one like type of ligand will be there. So how many such ligands of only one type is there in the compound? Or even if the two different types of ligands are there and suppose the coordination number is 6, so what will be possibility? One ligand is in one in number, another is in 5 in number. Then suppose ligand A and B are there and they are all monodentate. So ligand 1A, B5, or whether it is A2, B4, or A3, B3, or A4, B2, or A5, B in the case of heteroleptic complexes. What is the actual scenario? And this should actually be replicated into the name or IUPAC name of the compound itself. So that is what we call the appropriate multiplier. Means how many ligands of a particular type is there in the compound. And there are certain rules. The rules are now written here. The following rules are used when naming coordination compounds. The one common rule is, as we see also for the in the case of normal ionic compounds, the name of cation is always written first, and then the name of anion is written. So the compound's name is written in two parts. If there is a counter ion, cation or anion, then in that case the cation is always named first and then the name of anion will be given. And suppose both a cation here is just a normal ion, it is not a coordination entity or positive coordination entity, as you see in this case, cationic complex entity or cationic coordination entity, anionic coordination entity, neutral coordination entity. So what I mean to say is if the coordination entity is anionic. In that, the example that we have already seen, this is an anionic coordination entity. In the writing chemical formula one, if suppose someone has written K3 COCN6. If it is K3 COCN6, it means there is a cation which is potassium and then this is anionic coordination entity. So in that case, name of the potassium will be written first, which is cation. So it will be potassium. First we will write potassium and then name of this anionic coordination entity following the recommendation of IUPAC, as you can see here in this case. Or if the coordination entity is cationic, so we'll write the cation name of this coordination entity first, and then the counter name of the counter ion, as we saw in this case, pentaamine cobalt 3 sulfate. This is the cationic coordination entity. This one is cationic coordination entity, and after that we have just written the counter ion. So this is what it means. And if in this case, what the cationic and anionic coordination entities are there, is both the cations and anions are coordination compounds or kind of coordination ions. So in that case, the cationic coordination entity's name is written first, and then the anionic coordination entity's name will be written. So the cation is named first in both positively and negatively charged coordination complexes. This is a general rule everywhere, like NaCl. We have written NaCl, cation first and the anion. MgO, MgCl2, Al2, AlPO4, aluminum cation phosphate anion, Fe2, Fe2SO4 whole thrice, Fe, iron, it is iron plus 3 oxidation state, ferric form. So Fe, iron and then sulfate, and this is what is the common rule everywhere. Now let us look at the third rule. The dissimilar ligands are named in alphabetical order. So when the ligands are there and they are dissimilar, we'll follow their name should be written in alphabetical order, and it means the spelling of those names will be considered in deciding the alphabetical order. Like here, as you can see, carbonyl, chloro, di and tri we are not considering here, or this is triphenylphosphine. The name of the ligand is triphenylphosphine. So what will be the carbonyl? Ca. So it is written first, and this is CH. H comes later. So the carbonyl, the name of this ligand is written first, and even this numerical prefix is not considered here. The same rule is there in the diaphragm nomenclature of organic compounds as well. Numerical prefixes are not considered while deciding the alphabetical order, because they represent just the number of this ligand. This is not ligand, name of the ligand. So how many such ligands are there? It only represents. So this is a ligand carbonyl Ca. So carbonyl will be written first, and then the chloro or chlorido. This is usually we write as a chlorido, and then this is a triphenyl. This T. T comes late after C, and so it is written later on. What does it mean? The dissimilar. These are all dissimilar ligands, and so dissimilar ligands or different ligands, it will it should be the different ligands are named in alphabetical order before the name of the central metal or ion. I actually write different ligands, not dissimilar ligands. This their different ligands are named in alphabetical order before the name of the central metal. So the name of central metal is written later on. First we write the name of the ligand. As you can see in these cases, these are the IUPAC name of these complexes. And then the name of the metal at last is written. So on the prefixes mono, di, tri, as you can see here, tri, di are used to indicate the number of the individual ligands in the coordination entity. So how many ligands of a particular type are present in the coordination entity? To represent that, we use numerical prefixes di, tri, tetra, penta, hexa, and so on. So here, if the carbonyl is three such carbonyl groups are there, so we write tricarbonyl. Two chloro groups are here, chloro ligands are here, and two chloro ligands. So that's why we have two to represent two. The numerical prefix di is used, dichloro. So the numerical prefixes mono, di, tri, mono sometimes usually we don't write, but di, tri, etc. are used to indicate the number of individual ligands in coordination and taking. Then here we have used this to, to name that example. Let us see what this di, tri, tetra, and so on, tetra. So example is if the ligand is H2O whole 6, if this is written in the coordination, like if suppose in this case and some cases, the examples you might have seen this H2O whole 6, CrH2O whole 6. If the ligand is this, in this, then it is named as hexaaqua because hexa represents 6 and aqua represents the ligand. Name of this ligand, H2O ligand, is aqua. So it is hexaaqua. Please remember here there is a difference that we use usually the rule in IUPAC nomenclature of organic compound. Usually, if you write trialkyl or something, usually if the two vowels comes, the first vowel we omit usually in writing, and that we do not do the same thing here in the case of coordination compounds. You see hexa, it ends with A, and aqua, it starts with A. Usually in organic compounds, the naming IUPAC or writing the IUPAC name of organic compounds, we omit first vowel and then we write in this way. And however, in the case of this, we do not do like what is in on. If the in is also there in organic compound, the double bond is there, and on if it is also having a ketonic carbonyl group in the form of ketone. So what is the, if it is in on, so E of last E last E of in is omitted. So we write in En and One because the first vowel is omitted. In this case, we are not omitting. We are writing both A, both the A's. So this A also, this A also. This is tetraamine. Tetra again, tetra ends at A, and this is what it is ending at, starting at amine A. So this is both are actually written here. They are being kept. So this is one thing that you should not get confused. So the S2 whole 6 means it will be named as hexaaqua. NS3 whole 4 will be named as tetraamine. TO whole thrice is tricarbonyl. The example we have seen here in this case. This is Cl twice as a dichlorido. The chlorido and di numerical six just to represent this. CN5 pentacyanide, pentacyanide, and so on. This is what how we write use the numerical prefix as this. Then, but we have to take one thing in our mind. When the names of ligands include a numerical prefix, means the name of ligand itself contains a numerical prefix, then like example here, this triphenyl phosphate. This tri is what? It's the name. In the name itself, it's a numerical prefix. In that case, what will we use? Then the terms bis, tris, tetrakis, pentakis, hexakis, etc. are used to show the number of that particular kind of ligand, and the ligand to which they refer is placed in parenthesis. And the name of that ligand which is to which this tetracys represents, the name of that ligand is written in parenthesis, inside parenthesis, and as you can see here, the name of this ligand is written in parenthesis, and this is used to represent just that this two of such ligands, this ligand, two two triphenyl phosphine ligands are present in the complex. And this PPH3 represents polyatomic ligand, and so its name is written in the chemical formula in parentheses. And the name IUPAC name, this is just to represent this is the number, this is the ligand, and its number is 2 bis. So when the names of the ligand include a numerical prefix, then the term bis, tris, tetrakis are used, and the ligand to which they refer is placed in parenthesis. The name of that ligand is placed in parenthesis. For example, if you look En twice, En it represents the ethylene diamine, and the name of this complex is what? Ethylene diamine. We have di in the name of this ligand, not complex. This ligand, so it already contains diamine. So ethylene diamine, it has numerical prefix, and so if two such ligands are there, we write this and the name of this ligand in the parenthesis, ethylene diamine, and this is PPH3 size. So if the PPH3 size is there, we will name it as tree. This tree as we represent as trees, and PPH3 is the ligand, and the ligand in the parenthesis as triphenyl. This triphenyl phosphate. Names of the anionic ligand. The next names of the anionic ligands end in O. If the anionic ligands are there, their name will be ending in O. Like what is this chloride? Chloride is working as a ligand in this case. If you say its name will be ending as O, so it will become chlorido. This is cyanide, so it will be ending it will also be ending with O, and so it will become cyanido. Bromine, the bromide ligand, it will become bromido, iodido, chlorido, and so on. So, example, the halides is we use halide, and those of neutral and cationic ligands are same. The neutral and kinetic cationic ligands, we don't make any change. Only few ligands names are there. The exceptions are there. H2O, we don't write it as water, we write aqua. This ammonia we write as amine. You remember ammonia, the name of ammonia as a ligand is amine. This is amine. No, actually there will be double M in this case. So anyway, let us leave it here. I'll just correct it if there is any problem. Let me. Yes, it is double M. So 2M will be there in the name. So it was right. So this amine, this is ammonia, and it says amine. The carbonyl CO, carbon monoxide acts as a reagent which is neutral, and its name is carbonyl. This is nitrosyl. Nitrosyl is usually it is considered as NO plus as a ligand. So it is a considered as a cationic ligand. So this is nitrosyl. Other than that, if the CH3NH2 works as a ligand, this is methylamine, and the name will be written as such as this is what on those of neutral and cationic ligand will be the same, except the only thing is the same is the name of the molecule itself. It will be so it will be like methylamine and so on. You can see the examples here. Alkylamine, dialkylamine, trialkylamine. The name of the R is methyl group here, and it is dimethylamine. Or if it is methyl ethyl, so it will methyl ethylamine. Sorry, ethyl methylamine in the case in alphabet form. Ethyl methylamine, or even if you write methyl ethylamine, it will there will be no confusion, and so on. And this is pyridine. This is neutral, and the name of this molecule is pyridine. So this is the you can see which is written. The name is similarly same as pyridine. This molecule is what? It is piperidine, and so this name is in IUPAC nomenclature. Name of this ligand is also used. The same name, piperidine. However, in the case of you see, this is phosphide group, and this is it will become phosphido. This PH3 phosphine, the molecule, and the exception that we use again another exception is this name of the ligand is phosphine and so on. This is trialkyl phosphine and trialkyl phosphine and so on. So what happens usually? What rule we will have to follow is phosphine for phosphine and this. Just Okay. So phosphine for phosphine, nitrosyl for NO. For example, you can see here the example names of anionic ligands end in O and end with O, and those of neutral and the cationic ligands as the same. We write their name as same, except for few cases, as you can see some examples like for water, amine for ammonia, carbonyl for carbon monoxide, CO group, phosphine for phosphine, and nitrosyl for N. And for this NO is what? It is nitric oxide. Name of this compound is nitric oxide, or you can write nitrogen monoxide as well. So for example, if you look at this compound NiCl2 PPH3 twice, it is named as what? It will become dichloro. Chlorine is there, and the chloro Cl base chloro comes before this triphenyl phosphine. So C comes before P, and so this is dichloro, then a bis, and then in parenthesis we will start bis to represent this ligand, triphenyl phosphine close, and then name of the metal, as you can see in this case. If the complex ion is cation or anion, the metal is named as the same as the element. This is the one example. For example, if the complex ion is a cation, means the complex entity is cationic or electrically neutral. Whatever here I have said about is what is the charge on the ligand, whether it is negatively charged, ligand is negatively charged, or it is electrically neutral or cationic. If it is negatively charged ligand, it's negatively charged, its name will end at O. Normally, if you know the name of the ligand, you just add O at the last. Chloride, it will become chlorido. If you know the ligand, if it is cyanide, it will become cyanido. If it is bromide, it will become bromido. If it is amide, it will become amido. If it is azide, it will become azido. If it is phosphide, it will become phosphido. If it is oxide, it will become oxido, the name, because it is all these ligands are anionic. However, if the ligands are electrically neutral, we don't see anything. Whatever the name of the ligand is there, or even if it's cationic, we write the same name as such. And like here, this becomes chlorido. This is still phosphine, triphenyl phosphine. The name of this ligand is triphenyl phosphine, and we don't use O here or anything else here. It is written as such. So similar rules are there for the complex, even if the complex entity is cationic or anionic or neutral. If the complex entity, the coordination entity is cationic or neutral, we write the metal name of the metal as such. We don't make any difference. So if the cobalt is there in the cationic complex entity, then it will be written, it will end as cobalt. Or even if it is neutral, it will end at the same name. Like in the platinum and it is neutral or cationic, it will be platinum. And metal's name will be written as platinum. Here you can see here it is what we have written nickel, because the complex this complex entity is electrically neutral. It is having no charge on it. In this example, you see the molybdenum. It is electrically neutral. So there is we are writing simply molybdenum. However, if the complex entity is anionic. If the complex entity is anionic, then that is, as you see, this complex entity, this cationic also, this cobalt is written, the cobalt 3, simply. If the complex entity is anionic, and then the metal's name ends with suffix ATE. And just to represent all the ions, we write A8, sulfate, nitrate, bromate, chlorate, just to see the to make the similarity IOPC. Just however, the cations or the neutral atom the metals are not written AT or something. However, the anionic radicals usually 8 or I. Their name ends at 8 or I. 8 represents usually more oxygen atoms if it contains oxygen, and I represents less oxygen atoms. Like sulfate, SO4 is sulfate, so 4 2 minus is sulfate. The AT means it is having 4 oxygen atoms. Then it becomes, if I name beside sulfide, so it will have only 3 oxygen atoms. SO3 2 minus sulfide. Nitrate NO3 single minus, nitrite NO2 minus. So one oxygen is less. Chlorate ClO3 minus, chloride ClO2 minus. So AT usually, and in the case of anionic radicals, AT and I, these two terms we use, and you should remember these things as well. So for example, here cobalt is the complex anion, and in the complex anion cobalt is, this is the complex anion or the anionic coordination entity. In this case, the name of this metal will end at A, and what will be the name of this metal? The cobalt, and after the cobalt we will add At, so it will become cobaltate. If it was nickel, it will become nickelate. If it was copper, it will become cuprate. We use the Latin name here in the case of, because copper symbol that we write Cu. If it is electrically neutral, we will write simple copper, or the cationic, then also we write copper. If it is iron, so iron, if it is in the, means the iron is, if it is part of the neutral or cationic complex entity, then the name of the metal will be written as iron. However, if it is part of the anionic complex entity or the anionic coordination entity, then it will become ferrate. There we will use the Latin name. If the silver is part of the anionic complex entity, we write argentate. However, if the silver is part of the cationic or the neutral complex entity, we write simply silver. And so these things you should remember. So if the complex part is an anion, the central metal's name ends with the suffix "ate". For example, we have already seen how some metals, this is important point, Latin names are used in complex anions. Example, ferrate for Fe, cuprate for copper, argentate for silver, stannate for tin, and so on. The oxidation state for the metal in cation, anion, or neutral coordination compounds is indicated by a Roman numeral in parentheses, and as you see in these IUPAC names, the number 2 in Roman numerals in parentheses. I have never not explained till now what it means. It actually depicts the oxidation state of this metal. This nickel 2 means nickel here in this compound is in plus 2 oxidation state. In this case, molybdenum is in plus 2 oxidation state. Cobalt here is in plus 3 oxidation state. So to represent the oxidation state, we use the oxidation state in Roman numerals, and will put after the metal name of the metal in parentheses, just after the name of the metal, without making any gap there. Here I have just by mistake kept a gap. Let me remove it. So the, for example, cobalt in complex ion CuSCN4 is named as cobaltate 3, and how it will become cobaltate 3? Let us see the oxidation number of cobalt. Of course, SCN minus, one SCN ligand is thiocyanide ligand, and thiocyanide it is having one negative charge, and the entire complex is having two negative charge on it. So there is what? So two negative charge on it, how it will be? The C and SCN, four negative charge here and four negative charge here, and net on it is what? Let us write it like this. And so on. Now we can write it as it means there is one net negative charge on this complex, and if you don't see this charge on it, what will, there are four cyanide ions. Four cyanide ions will have four negative charge, and if they have four negative charge on it, and if the metal is having, what is the oxidation state of metal? Depending on the oxidation state of metal, metal will neutralize some of the anionic charges, and the net charge becomes one minus, and so what can we simply do is we add the oxidation state of the metal, suppose it is X, and plus 4 into minus 1. So x minus 4 is equal to minus 1. So x is equal to minus 1 plus 4, and so x is what? Plus 3. So oxidation state of cobalt in this complex will be 3. So and this is anionic complex, so we will write it as cobaltate 3. In this case, this is a neutral coordination entity or the neutral complex, and the neutral complex it will be the simply the name will not add at at the end of the name at the end of the metal's name, but oxidation state will have to represent, and this is electrically neutral. This compound is electrically neutral. Complex compound is electrically neutral. It means the chlorine, there are two chlorine ions, and the two chlorine ions must be electrically neutralized by it must be neutralized by the presence of plus 2 charge on the metal, and so the metal is having plus here in plus 2 oxidation state. So it is having plus 2. So nickel it will be represented as nickel 2. This in the Roman numerals 2 oxidation state will represent oxidation state. And so this is a common way, and you should also know to write the IUPAC name of of coordination compounds. You should also know how you will find out the oxidation number of the metal, and to find out the oxidation number of the metal, general criteria that we have discussed earlier to find out the oxidation number of the key compound, that will still be followed. And some other idea is just you will have to remove the ligand and remove the ligand. If the ligand is, you have to remember that ligand is X, those criteria will be there, whether it is X type or we call L type. L type means the ligand was having a lone pair of electron or not. If the ligand is having lone pair of electron, so it will not cause any positive charge on the ligand. And if the ligand is X type, means ammonia, water, they are coordinated through the lone pair of electrons. And if they are coordinated through the lone pair of electrons, so in that case, even if you remove these ligands, there will be no positive charge or any charge that will appear on the metal by removing such ligands. However, if the ligand is anionic, if they are not having the lone pair of electrons, not bound to the lone pair, like in the case of halides, usually the metal binds, atom binds there, the chlorine binds, it goes binds and binds. Actually, what will happen? Chlorine will remove one electron from the metal, it will accept one, it will become anionic. And once it becomes anionic, then it will donate its lone pair of electrons. Before that, it required one electron. So this way you can say chloride, like oxide, if oxygen is there. So oxygen requires two electrons, and it will first abstract two electrons from the metal, and once it abstracts two electrons, now we can donate one two lone pair of electrons to bind with the metal or one lone pair, whatever, depending on the structure or the composition of the coordination compound. And so on. If the hydride is there, hydrogen is also a non-metal, and it is having one odd pair of electron hydrogen atom. So it will abstract one electron from the metal and causing metal becoming plus one, having one plus one charge, and this hydrogen will become hydride H minus. And now this electron which will behave as a lone pair of electrons in hydride, the hydride can donate to metal. And so if you want to if you remove that metal, it will come out with the electron, and that one electron of the metal as well will come out with the hydrogen. And so this is the way you can find out the oxidation number of the metal. And simply, so simple things are two ways, two types of ligands you have to understand, whether the ligand is L type or X type. L type ligand means the ligand is having a lone pair of electrons, and ligand is coordinated. Both the electrons that are sharing with the metal are only of the ligand. However, if the ligand is something that it has deficiency of one electron, and now if it goes there and it when it forms a covalent bond with the metal, we know the covalent bonds and the electronegativity difference. Metals are having very low electronegativity, non-metals having very high electronegativity. So the both the electron pairs will be shifted to the ligand, and if you remove this ligand, so heterolytic cleavage will happen. Ligand will come out with the both the shared pair of electron, it will be having negative charge on it, and the ligand will correspondingly get a positive charge on it to make the total, sorry, metal will get positive charge correspondingly on it to have the net charge to make the net charge zero on the entire computer. So anyway, on the entire system. So there are certain rules that one should follow to find out the oxidation number. I'll try to discuss it on one day in details. I'll write out the rules and then we'll discuss with certain examples to find out the oxidation number. So the oxidation number is important to finding out the oxidation number of metal is in a complex compound is important. The name of the complex part is written as one word. So everywhere that we have seen here, the complex part is written as one word. The entire thing is written as one word here to here. Again, in this example, you can see this is one word. Here, the complex part is one word and the counter ion is written as a different word. So there is a space. One word means there is no gap. So the name of complex part is written as one word. There should be a space between the name of complex ion and the counter ion. So we deliberately put one space just to distinguish whether this ion or the another name that we are taking is the complex means is just a counter ion and it is not a ligand. If I'm not confused it with the ligand. For example, chlorine, you see this complex. Yes, not here like this complex. To write this complex. The chlorine here is also in the coordination entity. Coordination sphere means chlorine is behaving as a ligand and chlorine is also behaving as a counter ion. So to just understand whether this which chlorine is counter ion and which chlorine and how many chlorine behaves as a ligand, to understand we provide a space. And also whether you have understood the rules or not, or whether this will become chloride or this will be chloride, but this will be chloride. This will be represented in the name, it will become chloride. Like the name of this complex ion will be pentaamine, because amine A comes first. Pentaamine chlorido, pentaamine chlorido, cobalt in bracket in parenthesis 3 chloride. Simply chloride. Last. And these are some ligands, name of the ligands. So ligands, their common name and IUPAC name. This is hydride. Hydrogen ligands are always considered anionic. So it's hydrogen ligand is, it will always be anionic, considered like chloride, bromide, iodide. You should always consider them as unique. And now this anionic ligand will donate its lone pair of electrons to the metal. So once that bond is broken, it will come out with the entire electron. So anyway, that will be metal. And if this ligand is going to and binding to the metal and entire complex is electrically neutral, it means there is plus one charge on the metal. That is why it has valence negative charge of this ligand. So anyway, this is or hydrido. Common name is hydrido, and IUPAC name is also hydrido. People also, and this fluoro called this we call this ligand is called fluoro. This complex called fluoro complex, bromo complex, iodo complex, commonly cyano complex. But in IUPAC name, what we will write the name? This is hydride, so it will become hydrido. Fluorine, the chloride ion. This is chloride ion, so it will become chlorido, chloride ion, chlorido, bromide ion, bromido, iodide ion, iodido, cyanide ion. It becomes cyanido. And cyanide ion, there are two possibilities. It can metal can bound through carbon and can also bound through the nitrogen. So this is ambidentate ligand, and antidentate ligand. Carbon can also act as a donor. Nitrogen can also act as a donor. So this is cyano, and if it is NC, MNC, it is called isocyano commonly. The cyano complex, and one can write the name of this as cyanido or cyanido kappa C. Kappa represents the this means the C is bound to the carbon, or simply cyanido C. Sometimes people also say cyanido C. If the Cn minus is there but it is bound to nitrogen atom to the metal, then this group is called isocyano. Or isocyano, the name will or isocyanide. This is an ion is isocyanide. Nc minus ion is isocyanide, and so it will IUPAC name will be isocyanide or Cyanido, if you are writing cyanido, then you will have to write N. Cyanido dash N. You can also write cyanido as you can see here. The cyanido, if it is C, so it is C. And if cyanido N means it is isocyanide, which is having, acting as a ligand. This is what this is a methyl isocyanide. And the methyl isocyanide. This is electrically neutral, so O will not be added here. So methyl isocyanide. This is what this is azide. The azide is the ligand N3 and minus. N3 single minus is called azide, and the common name of this ligand, if it can behave as a ligand, is called azido, and the IUPAC name will also be azido. And the ligand is azide. And the azide, from azide you write O, remove E, and write O, azido, it will become azido, and so on. The ligand, this their SCN minus this thiocyanate, and thiocyanate you will end with the thiocyanate, but the thiocyanate, as we know, it's a bidentate ligand, so it can coordinate through sulfur as well as nitrogen. If it is coordinating through sulfur, then we will call it a thiocyanatoase in our PAC name. We'll write it as thiocyanatoase. Or if it is nitrogen, which is donor, as you see this coordination MNCase, then it will be thiocyanatoN. Or isothiocyanoto is also there. You can also write isothiocyanoto or thiocyanoto. This is what it is acetate group, and if it is behaving as a ligand, it will be acetato. And the IUPAC name, this is what ethanoate ion. This is ethanoate ion is as per the IUPAC nomenclature of organic anions. Organic means the carboxylic acid anions, and the carboxylic acid anions is like 8 we like carboxylate, so it is right as a carboxylate. This is ethane, two carbon atoms, 1 2, so ethane and O80 for this anion, so ethane noate. So this is ethanoate is the name of this anion, IUPAC name of the anion, and the ethanoate, from ethanoate it has become ethanoate. Now see N3 minus, this is 3 minus, 3 negative charge on one nitrogen atom. Here what you have seen, three nitrogen atoms bound together and one having one negative charge. This is one nitrogen atom having three negative charge. This is nitride, and nitride become nitrido, and so on. This amide, this is not important. This is amide, NH2 minus, and amide will become amido or azanido. People will also write it as azanido, or you can also write it amido. This is amine. Amine. This is neutral, so amine, and so on. These examples we have already seen, and so on. This is, you can see oxo. This is the common name of this ligand is called oxo, but in IUPAC name we write it as oxido. This the hydroxide ion is there. Hydroxo, the ligand we call is hydroxo ligand, but the name in the IUPAC name we write it as hydroxido, because the anion is hydroxide, and hydroxide ion is working as a ligand, so it is hydroxido in IUPAC nomenclature. However, the complex normally called hydroxo complex means the OH group is acting as a, means hydroxide ion is acting as a ligand. Water, aqua that you know, H2 sulfur, and so on. These are not much important. O2, which is dioxygen, electrically neutral, so we can, let's call dioxygen. This is carbonyl, and the carbonyl is the name for this. Other things, nitrite, you can see the example of nitrite we have already seen, nitrite so N and nitrite so O. This is nitro. NO2, nitrogen is the ligand, nitrogen is the donor, so it can also be called a nitro complex. And if or the nitrite to N, and if oxygen is the donor, then we can also call nitrito O or nitrito complex. If this is nitro, this will be called as nitrito, or this name will be the nitrito O, and so on. There are some common chelating ligands. It's a very famous, very robust ligand by NEP to the optically active. You don't have to study about this. Remember 2,2-bipyridine, the BPY or bi we write. This is 2,2-bipyridine, bidentate ligand. Here we are just now we have started looking at the bidentate ligand. This is bidentate. This is bidentate. This is also bidentate ligand. Just to see, this is also cyclopentadiene. Now this is also bidentate ligand. One this group and one other donor will be the nitrogen. This You can see here it is a bidentate ligand. The two nitrogen donor atoms are here. This is also a bidentate ligand. This is also a bidentate ligand. Acetyl acetone, two important ligand. ACAC, the common name is ACAC. This is acetyl acetonato. Acetyl acetone. If you remember acetyl acetone, and if you just remove one proton from there, it will become acetyl acetone. So this will become acetyl acetonato. So just remove from this acetyl acetone one. This is methylene active methylene group. From here you just remove one proton, and there will be negative charge. That negative charge will be in conjugation with this double bond and as well as this double bond. And so what you see that is that negative charge is delocalized over all the atoms here, here, here. So the delocalization is represented as this and this. So this is acetyl acetone NATO ligand. This ligand is ethylene diamine or ethane 1,2 diamine. So ethylene diamine represented as EN. This is a just simple representation or abbreviation of these ligands. As you can see, so oxalato is another important complex. This NAC complex is also a very important complex, but you don't have to worry about this complex. Not necessary for you to remember its name. These ligands are now the tridentate ligands. You can see this is tridentate ligand, tridentate ligand. So tridentate, this is a tetradentate ligand. Now we started tetradentate ligand, tetradentate ligand. These are all tetradentate ligands. Tetradentate ligand. This is the porphyrin ring. If you remember the tetradentate ligand, tetradentate. All these ligands are tetradentate. Four donor groups as a nitrogen having lone pair of electrons. So you can easily understand tetradentate ligands. All one donor, one donor, one donor. Four total four donors. This is now becomes pentadentate ligand. This is pentadentate ligand. This is not tetradentate but pentadentate ligand. This is also pentadentate. One, two, three, four, five pentadentate ligand. Because nitrogen, each nitrogen has a lone pair. Here, oxygen also has five oxygen atoms. Six oxygen atoms are here in this case. This is 18 from 6. This is an important molecule, molecular formula. This is a hexadentate ligand. Hexadentate ligand is this one as well. One, two, three, four, five, six. This one is 1, 2, 3, 4, 5, 6. Also hexadentate ligand. Please remember, in the case of oxalate or sorry acetate ion, only one oxygen acts as a donor, not to both the oxygen. Although this oxygen also has a lone pair of electrons, but because of the geometrical constraints, it doesn't behave as a donor. So this oxalate, although it has two donor atoms, but this one behaves as a monodentate ligand only. And one can consider this as a kind of ambidentate part because this the negative charge is delocalized, so this one atom can also behave if the symmetrical possibility is there. It can behave as also as a ligand. So anyway, so this is now becomes heptadentate ligand. One, two, three, four, five, six, seven donor atoms. In this case, one, two, three, four, five, six, seven, eight is the octadentate ligand. This is 1, 2, 3, 4, 5, 6, 7, 8 is also octadentate ligand and so on. You can see. Let us now see some examples. Write the IUPAC name of this complex. So what will be the IUPAC name of this complex? We'll write the name of the cation first, and the cation here is this is the coordination entity is cationic. In this case, and that's the counter ion. So we'll write the name of the cationic coordination entity first and then the name of the counter ion. And see, we simply write the name of the counter ion only. Its number is not required to represent here in the case. You see, in the case of ionic compounds, we write MgCl2. This my name is magnesium chloride. We don't write magnesium dichloride. It's MgCl2. And why it is so? Because of the valency and the charge on the cation and anion, one can easily understand what will be the molecular formula. Like if I'm saying magnesium chloride, I know what will be the valency of positive charge on magnesium. It is +2, and so to neutralize this, I need two chloride ions. So I always write it as NgCl2. Like FeCl3, it is ferric chloride. If the ferric is having +3 charge on it, and if I know ferric, it is having +3 charge, so I require 3 charge, but we call ferric chloride. We don't write ferric trichloride. So similarly here also, even though here three chloride ions are there as a counter ion, we will write only one chloride, simple chloride, because if you know the charge on this cation, the complex cationic complex entity, we will simply understand how many chloride ions will be there in the molecular formula. So that is a common sense thing. And so what will be the name? The name will be first, we will write the name of the ligands, and that too in the alphabetical order. So what is the ligand? Amine. This is amine. This is aqua. N comes before Q. At the first place, there is no difference aqua and amine, but N comes first at the second place, then Q, and so amine name of this ligand will be written first. So this will be triamine because three amines are here. Triamine, triaqua, chromium, and the oxidation state of chromium will be what? Plus 3 because this is a neutral ligand. This is neutral ligand. However, three chloride ions are there means it must be having plus 3 charge on it. And so the chromium 3, this is chromium 3, this is cationic, so we will not add AT at the end. Chromium 3 chloride simply. The description is written here, you can read it out. Let's see next question. We have to write IUPAC name of this complex compound as well. So PT H2N CH2 CH2NH2. To recognize this ligand, it is ethylene diamine. One can also write it as EN. So this is ethylene diamine. So E is the first letter, and this is fluorine. Fluoro is the first letter. So fluorine comes first, and the two fluorine atoms are here. So two chloride ligands are here. So ligands are only chloride in this case. So the two chloride ligand. So we'll write dichloro, as you can see, dichloro, and then this is what the name of this is ethylene diamine. The name itself contains numerical prefix. So in that case, to represent it is two in number. So to represent its repetitiveness, we'll use bis, and so bis and the name of this ligand will be written in parentheses as we have seen the rule. So this ethylene diamine, and then platinum, because this is what? This is positively charged complex. The positive coordination entity is here. So the platinum and the oxidation state of platinum we will have to write. And then the chloride space here and to write the this counter and chloride. And how will we find out the oxidation number? This is electrically neutral ligand, as you can see. This is lone pair, it coordinates to the lone pair. This chloride. Chloride is electrically negative ligand. So two chloride ions are two negative charge, and those two negative charge are balanced by charge on plus charge on this platinum, and two negative ions are here. These are two negative ions, these are two negative ligands. So these are two ions. Because of these two ions, there will be two plus charge on this coordination entity. Plus two charge is there despite having two chloride ions. So it means platinum must be having plus four charge on it. It means its oxidation state is plus four. So dichloro bis ethylene diamine in parenthesis platinum 4 chloride will be the name of this complex. Another, the description a little bit description is given here. The name of this complex, let us see what is it. This is again ethylene diamine, the ligand, but it is 3 in number and 3 in number, and also you can see this complex. The twice is written here. Why twice is written here as a subscript after the square bracket? Because this represents two such complexes are required to balance the charge of three sulfate ions. It simply means as we write A mm, uh, like Al2SO4 whole size, Al2SO4, this is aluminum sulfate, or Fe2SO4 whole size. So it means what? The Fe was having plus 3 charge on it, or the aluminum was having plus 3 charge on it, and the charge anyway that we exchange here. So this it means this complex entity is having plus 3 charge on it, and this plus 3 charge will help us to find out the oxidation number of cobalt. So plus 3 charge over here, for this ligand there is only one type of ligand, and that ligand is electrically neutral, and whatever its number may be, it will not contribute anything to the oxidation state of the metal. So there is, so what is the whatever the plus 3 charge that will appear on this complex entity, that will only be because of the plus charge on the cobalt, and so cobalt here is in plus 3 oxidation state. And the name of this complex will be, this is what this ligand name contains numerical prefix. It is ethylene diamine. Di is there, so we'll write tris in this case to represent its number, and this is 3. So tris means 3, so it will be tris, and then name of this ligand in parenthesis ethylene diamine, and then cobalt in plus 3 oxidation state. It is here, and then sulfate is the name. There are some other examples as well, and these examples will see in our next lecture. I'll stop this lecture here, and then after that, we'll see also, we will see the isomerism in coordination compounds. However, one thing I have not explained here is how the name of a compound will change in the case of isomers, because one can have different type of isomers as well, because you will not understand this because I have not explained isomerism in the case of coordination compounds. So those rules I have not explained. Once I'll explain this, I'll also include those rules, how will you difference between the names of two different isomers. And isomers means what? The same molecular formula but different structure, and different structures have the different, the structure is different means the name should also be different, because the name should actually uniquely or unambiguously represent the structure of the given complex compound as per the rules of the recommendation of the IUPAC. Those things we'll see in our next lecture. I'll stop it here. Okay, bye.